Now that you've seen what the electric field is, I want to give you a few examples of calculating it. So imagine here a charge. I'll arbitrarily assign this value of this charge plus 2 microcoulombs. And let's just say we want to find the electric field at a point above the charge, and let's say it's 30 centimeters above the charge. The equation for the electric field, the strength of the electric field, is going to be given by K times Q divided by R squared. It looks a lot like Coulomb's law, except there's only one charge here because one charge will create an electric field. So that's 9 times 10 to the 9th times 2 times 10 to the minus 6 divided by, and 30 centimeters is 0.3 meters squared. So I have, on top I have 18 times 10 to the 3rd. On the bottom I have 9 times 10 to the minus 2. So this gives me 2 times 10 to the 5th newtons per coulomb. That's how strong the electric field is. So the strength of it I express by taking the magnitude of the vector. You can also just write it as E. So once I take the magnitude of the vector, get rid of the vector sign, that this just represents a strength or a magnitude. All right, now what's the direction? Well, if I were a positive charge at the point X, I would experience an upward force. So that tells me that the direction of the electric field is upward, or J hat. All right? I want to do a similar example, but this time I want to put the point of interest same distance away, but at an angle of 30 degrees. Let's just try 30 degrees from here. But the distance is still 0.3 meters or 30 centimeters. Okay, so find electric field at that point. Well, I can go ahead and use Coulomb's law. I'll write it again just to try to cement it in your memory. But I'm going to get the same value. I'm still going to get 2 times 10 to the 5th newtons per coulomb. That looks like a big number, by the way. Electric fields tend to be big because when you multiply by small charges, then you get reasonable sized forces. But electric fields tend to be pretty big numbers like you see here. But in any case, it's the same value as what we had up here because it's the same distance. 30 centimeters here, 30 centimeters there. The difference is that the angle is this way. So the direction of the electric field is not going to be vertical. It's going to have both a vertical and a horizontal component. I need to figure out what those are so that I can express this electric field vector in both I hat and J hat. I could say it's at an angle of 30 degrees, that the electric field is 30 degrees above the horizontal. So I could say this. But for reasons we'll see, sometimes we need to express them as I hat and J hat. So that's what I'm going to show you how to do. So here's my vector, 30 degrees above horizontal, and it has a value of 2 times 10 to the 5th. And what I need to do is determine its y component and its x component. I'll call this EX, and I'll call this one EY. And the way I'm going to find that is I'm going to say, this is units of newtons per coulomb. I'll say EX. Let me clean up this E. And EY. And both of these, I would argue, in this case, are going to be positive because x points to the right and y points up. But we need to be able to account for that sometimes we'll have to put a negative sign in front of them. So I just have to solve for cosine of 30 times 2 times 10 to the 5th, and then I'll have my answer. So EX equals 2 times 10 to the 5th times 0.866 newtons per coulomb I hat. That's going to be equal to, let's see, that's EX. EY is 2 times 10 to the 5th times the sine of 30 degrees, which is a half, newtons per coulomb J hat. So that's going to be equal to 1 times 10 to the 5th newtons per coulomb J hat. Okay, so there's my X component and my Y component of my electric field. And that's the problem completed. So hopefully you see how you can calculate the electric field at any point in space from a single point charge whose value you know. You can figure out at any point what the strength of the electric field will be and what its direction will be as caused by that single point.